Welcome. This is Coach Dorf. Today, we're going to have an introduction to the idea of limits of functions. What are the two main ideas of calculus? They are derivatives and integrals. And so we're going to ask, what are derivatives? Well, let's look at this in terms of a function, a graph of a function. So suppose I have a graph of a function that looks like this. We'll call this y equals f of x. We're going to take a point on here, right here. We're going to call this point x1, y1. So here's x1, and there's the y1 value is here. All right. I want to do in calculus for derivatives is I want to find the slope of this green line. What is the slope of that line? That line is called a tangent line, and it only intersects the blue curve of the function near that point x1. It only intersects it at one point. Now we know from before calculus, so like in algebra, that if I had 2 points, I could find the slope of a line. But here we only have 1 point. We have that one red point. We don't have any other points to figure out the slope. So how can I figure out that slope? Well, if we go back to before calculus, like we said, if we had 2 points, we could figure out the slope. So let's just take another point on the graph of the function. All right, let's take, for example, this point right here. We'll call this point x2, y2. And I can connect the red point and the purple point here, and I can compute the slope of that line. The slope is going to be the differences of the y's over the differences of the x's, all right? And so I can find the slope of that orangish yellow line there, the golden line. Now, is that going to be the same slope as the green line, the tangent line? No, it's not, okay? But it is the slope of a line, and it gives me a slope of a line. But how can I make it better, or how can I make it closer to the slope of the green line? Well, if we take another point that's a little bit closer. So instead of using that purple point, let's take this darker green point. We'll call this x3, y3. And we're going to look at the slope of that line, and let's use a purple line there. So we're going to connect the red and the dark green one, and I can figure out the slope of that line. And the slope of that line is going to be the differences of the y's over the differences of the x's. And what do I notice about the slope of the purple line compared to the slope of the gold line and the slope of the green line? Well, the slope of the purple line is closer to the slope of the green line than was the slope of the yellow line to the green line. So I'm getting, by making my point x3 closer to my initial point, my red point, I'm getting a better slope. And the idea is now I'm going to keep taking more and more points. So if I take another point closer and closer, right? And as I do that, I'm going to get a better and better approximation of the slope of the tangent line, the slope of that green line. All right. This idea here is the idea of getting closer and closer to a point is known as the limits. Right, the limit, and it's written as limit as x gets closer to x1 of my function, and that's going to equal L, and L is going to represent the limit. And starts L, the first letter in the word limit is an L, so that's why we give it that capital L there, and that's going to be a number. Okay, that's as we get as we get the points x get closer and closer to x1, then we get a limit there, and that's going to allow us then to get closer and closer to the slope of the tangent line. Okay, let's look at example here. So suppose I have location or position, sometimes it's called that, of an object is given by a certain function, and we'll call that y equals 3 minus 1/2 x squared. And that's given as feet there. Sorry. Okay. I want to find the average velocity over following intervals. Okay, I'm going to have some intervals here. We're going to have interval 1 to 2. We'll have the interval from 1 to 1.5. We'll have the interval from 1 to 1.1. And we'll have the interval from 1 to 1.01. Okay, before we answer this one, we need to talk about what do I mean by average velocity? So before calculus, all right, the slope of the secant lines, an approximate value of the slope of the tangent line. And this is also known as the average rate of change or average velocity. And again, what is that secant line? Maybe I didn't say that before, so let me talk about that. If my curve here looks like this, and I'm trying to find slope of this tangent line here, and this is the tangent line, then when I take a different point, like that purple one there, and I did this, okay, slope, we said was the differences of the y's over the differences of the x's. This is known as the secant line. All right, so the tangent line is the green line. We only have 1 point. The secant line is the one where we have the 2 points, the orange gold color line here. So before calculus, we could compute the slope of the secant line because we had 2 points. And that's equal to the approximate value of the slope of the tangent line. Also can be represented as, or talked about as, the average rate of change or the average velocity. After calculus, or with calculus, what do we have? The idea of limits. So using limits, the idea of getting closer and closer as our purple point gets closer and closer to the red one, that's the limit. Using the limit, we can get then the slope, we get the slope of the tangent line, and that is expressed as the velocity or the rate of change. Okay, going back to this original problem now here, this example, I have the location or position of the object, and it's given by this function, and I want to find the average velocity over the following intervals. Okay, that means we're going to be doing the before calculus steps here. All right, we're going to be finding the average velocity. Okay, we find the slope of the tangent lines. All right, so again, my function here is y equals minus 1/2 x squared. And I'm going to do the interval 1 to 2. So that means it is 1. Okay. And then I have to figure out what y1 is. So y1 equals 3 minus 1/2. I put in what x1 is, which is 1. Okay. And I end up with 2.5. So I have the point 1 comma 2.5. And then I take my second point, x value, which is 2, right? Just to make sure this is clear. This one is this. This 2 is this. And then what's y2? Well, I take the same equation, 3 minus 1/2 x, and I put in 2 for x this time, this. And when I do that, I end up with a value of 1. So what is I want to find out what is the average velocity. So the average velocity equals this, which is y2 minus y1 over x2 minus x1. And in this case, then that's going to be minus 2.5 over 2 minus 1. And we're just to make sure we all understand, this one gives me this. This 2.5 gives me this. This 2 is from here, and this 1 gives me that right there. The differences of the y's over the differences of the x's. And when I simplify that, that all then becomes negative 1.5. So that's that average velocity or the slope of the secant line for the interval 1 to 2. Now I can keep doing this for the other values. So I have 1 comma 1.5. So here then x sub 1 is 1, and I can solve for y sub 1 and doing the same way I did before. And when I do that, I'm going to come up with, because that's the same as what we had before. And then I do x2 is 1.5, and then I come up with y sub 2. And when I do that, I come up with 1.875. And so then the average velocity or the slope of the secant line, and again, is going to be y2 minus y1 over x2 minus x1, and I'll have 1.875 minus 2.5 over 1.5 minus 1, which when I simplify that, I come up with negative 1.25. I keep doing this. Let me show you a way to help you in doing this. Okay. There is a program that, or a site that I use online. I recommend it. You can use anything you want to. You can use your own calculators, but this, if you don't have a calculator, which most of you probably don't, you could use this site called Desmos. This is the one that I use. And you can see here, they have different math tools. I'm going to use the scientific calculator one here. All right. And I can put in the values of function here to figure out what things are. So I've done a little bit of that up here. Let me just set this up so we can see. So I wanted to figure out the value of the function way back when x was 1. So I put in the value 1 here into my function. My function was 3 minus 1/2 x squared. So I put in 1, and over here comes out that y value 2.5. All right. Then the next one, we put in 2. So when I have x is 2 here into my function, I come up with the value 1 over here. And so with those values, then I can figure out the average velocity or the slope of the tangent line by doing the differences of the y's. So here is y2 minus y1 over here. There's y2, there's y1. And then I put it over x1, x2, which is up here, minus x1, which is up here. And it gives me that value of negative 1.5 that I showed you on the iPad earlier. All right. And then I can just keep doing this. Next example, let me put this up here so it's easier to see. Again, I do x1 is 1, and this time I did x2 as 1.5, came out with these values, put them into this equation here, and I get into this expression here, and I get negative 1.25. Likewise, I can just keep doing it, 1 and 1.1, and I come up with my average velocity, negative 1.5. And then the last one, I'm putting in 1 for x and also still doing the 1. And when I put in those values here, I get out and the average velocity as negative 1.05. Okay, so this is a way you can do it when you need a calculator. Just use something like Desmos, or you can use any other sites, but Desmos I think works well. All right. Going back now to my iPad, we use this information here. Okay. Up here, from what I just had here when I did this one, so from Desmos, we came up with the velocity in this case was negative 1.05, and using 1.01 from Desmos, the average velocity was negative 1.005. So if I look at these values here, again, what I'm doing, notice here with my x values, I've got 1 using 2, and then I'm doing 1.5, and then I'm doing 1.1, I'm doing 1.01. So x is getting closer to 1. And then the average velocity, what's happening there? Well, let's look at those values. We'll look at those in red. So we had negative 1.5, then we had negative 1.25, then negative 1.05, then negative 1.005. So it looks like that's getting closer to negative 1. All right. And so we could say that we estimate at this point, estimate that the instantaneous velocity of the function y equals 3 minus 1/2 x squared, x equals 1, is negative 1 feet per second. Okay, an estimate because we don't know for sure, but it sure looks like those red circles. I'm going negative 1.5, negative 1.25, negative 1.05, negative 1.005. It's getting closer and closer to negative 1 as x gets closer to 1, which are the green circles there. All right. So the values we computed were the average velocities, and then we're guessing or estimating that the instantaneous velocity would be negative 1. That's all we can do right now. alert here, okay, we'll find a way to actually figure out and show that the instantaneous velocity is -1, but you're going to have to wait on that one for a little bit before we get to that. Okay, this leads us to now. Okay, the idea of limits is essential in developing derivatives. Okay, so we need to talk. We're going to put away the idea of derivatives for a moment here and the slopes of the tangent lines. We're going to put that on hold because we first need to understand the idea of limits more. So going to be like almost like a commercial break here. We're going to talk about, for the next lessons, we're going to talk about limits. So we better understand the idea of limits. And then we're going to use that idea of limits to understand derivatives. So again, just to keep the big picture in mind, the two main ideas of calculus are derivatives and integrals. But now we're going to put those on hold so we can talk about limits, so that then we can use the idea of limits to actually understand derivatives and derive the idea of derivatives. Okay, we're talking about now, this is our topic for the next few times. And let's look at some examples here. I'm going to call this example number 1, even though we just did an example. I'm going to have a function f of x equals x minus 1. All right, and what does the graph of that function look like? All right, so that's going to look something like this. If I have some points here, this is the point 1, this is the point 2, this is the point 3, here's my x-axis, my y-axis here, here's point 1, here's point 2, all right, and this is the point -1, and here we have -1. Okay, I want to understand the limit. What is the limit as x goes to 2 of x minus 1, this function here? So let's just look, if we made a chart of values, I want to be getting close to x going to 2. So we're going to put in some values, aren't at 2, but getting closer to 2. So we could do 3, 2.5, 2.1, maybe 2.01. And then we want to look at what is, do that in black. So with f of x, which is x minus 1. When I do that, what values do I get? Some green values here. When I put in 3, I'm going to get 2, because 3 minus 1 gives me 2. When I put in 2.5, I'm going to get 1.5. When I put in 2.1, I'm going to get 1.1. And when I put 2.1 in, I get 1.01. And so these keep going, just like these keep going. And so what's happening here is we're getting close to what value? Well, the green values are getting close to 1, as the red values are getting closer to 2. So we guess that the limit as x goes to 2 of x minus 1 equals 1. All right, we're just guessing now because we haven't formally talked about how we can do this. All right, so then let's do another example. Example 2, here we're going to have the function f of x equals x squared minus 3x plus 2 over x minus 2. And what's the graph of this function look like? It's similar to the previous one. May not look like that at first, but it is. And it's going to look like this. All right. There's going to be actually be an open circle at right there. And then the function is going to look like that. Graph of the function. So notice, how is that different than the first one? It's exactly the same as the first one, except that when x equals 2, there's a hole there, because I can't put in my function here, I've circled in red here, I can't have the value x equals 2 because then I'd have a 0 in the denominator. Okay, function's not, it's not part of the domain. Remember when we talked about the domain, if you have a fraction representation, which is known as a rational function, you can't have 0 in the denominator. All right. If I put in x equals 2, I have a 0 denominator. So I have to have a hole in the graph there in this case. All right. We want to do the same thing here. We want to figure out what is the limit as x goes to 2 of this function x squared minus 3x plus 2 over x minus 2. What does that limit equal? And just like the previous one, we're going to make values. And you may say, how do I make this table of values? I could just use Desmos and compute them out. So I'm going to start with 3, then go to 2.5, go to 2.1, 2.01, just like we did before. And in computing these, it's consistent. I'm going to use green here. All right, I'm going to come up with, when x is 3, in this case, I'm going to get f of x is 2. When x is 2.5, I get 1.5, and then just keep going down. I get 1.1, 1.01, dot, dot, dot. Okay, actually the same values that I had in the previous example. And so what do we have here? We can say that as, okay, close to 1. So my limit is getting close to 1. These are getting close to 1 as the x is getting closer to 2, which is what this idea is here. This limit as x is going to 2, okay? What we have here, as I'm doing that, my green values are getting close to 1. So we say, we guess that the limit, the word s there, the limit as x goes to 2, x squared minus 3x, that's the word 3, also plus 2 all over x minus 2 is going to equal 1, okay? Note that is exactly the same as the previous one, previous example, okay? Function, the graph's the same except I have a hole there, and we get the same limit value. Okay. One last example here, my function f of x is going to equal this strange type of expression here. This is known as a piecewise function. I've got two pieces of it. When x does not equal 2, it's going to equal this x squared minus 3x plus 2 all over x minus 2. And when x equals 2, we're going to say it's equal to 0. And what's the graph of this one look like? Again, it's going to be similar to the previous one. You go up like this. I have a hole here like that, because that's the first part. Because x for the x squared minus 3x plus 2 all over x minus 2 can't equal 2. I have a hole there. All right. But then the second part of the function here, it tells me that the value of the function is going to be 0 when x is 2. So it looks like this. So put a little hole there. Again, this is called a piecewise function. There's two pieces, and we have that big squirrely bracket there. So, okay, now we're going to do the same thing. We want to look at the limit as x goes to 2 of f of x here. And what does that equal? So we can do a chart just like or a table like we did before. We're going to use the same values here. So we're going to have 3, 2.5, 2.1, 2.01, and then we have f of x here. We're going to use the same values there. And when we do that, we get 2, 1.5, 1.1, 1.01. Again, you can just put these values in. How would I put these values in? Well, when x is through, let's say here, I just go to this function. X is 3, I'm in the top part of my piecewise function. Okay, that's always true as long as x doesn't equal 2. So then when I put 3 in there, the numerator, I'm going to get 3 squared minus 3 times 3, 2. That's going to then give me a value of 2 on the top. And when I put 3 in the denominator, I get 3 minus 2, which is 1. So I get 2 over 1, which gives me then my value of 2. And I do that for all these things here. All right, so what do I notice is happening? As x is getting, x gets close to 2, okay, x gets close to 1. And so again, we guess the limit as x goes to 2 of f of x is going to equal 1. So notice it happens, it's the same thing for all of 3 of these examples here, even though they're slightly different functions. So what do we learn? What do we learn from these? Oh, sorry. Let me rewrite that. What do we learn? What do we learn from these examples? And this is the main point here. What do we learn? That the behavior of f of x for x near 2 is what is important when limits. All right. It doesn't matter what happens exactly at 2. What's important is when we get close to 2. Okay. Notice in the first example here, when x equals 2, we have a certain value, and that's perfectly fine. But in the second example, we don't have a value for x equaling 2, but it didn't matter. We still got the same. We got the value of the limit, and it was the same as the previous one. And in the third example, the value of x when value of f of x when x was 2 was a totally different value, and that didn't change the limit. The limit was still the same as in the previous two examples. Okay, let me see if I can demonstrate this with then diagram. Or another example, function that looks a little bit different here. So we're going to have this function, looks like this, have a hole here, this in, and we're going to have this here. So here's going to be your value of 1, here's the value of 2, here's 1, x equals 2, x equals 3, be -1, and this will be -2. Okay, there's my graph of my function. It's really kind of a weird function, but that's what it is. And we want to determine the following limits. So what is the limit as x approaches 3 of f of x? Well, as I get really close to 3 here, if I look what's happening here, the value of the function is near 2. So that's going to equal 2. All right. How about if I do the limit as x approaches -2 of f of x? What's going to happen there? Well, the function's not defined at x equals 2. There's that open hole there. But that doesn't matter. That was just like example number 2. So this is like 2 up above. This first one was like number 1. So like 2, it doesn't matter what happens exactly when x equals -2. It only matters what happens when it's close. And when it gets close, it has a value of 1. All right. What about the limit as x approaches 1 of f of x? Well, this is like, that's right here, and that's like 3 up above. Okay. What does that equal? It doesn't matter that I have a hole there. It doesn't matter that I have a filled in value above it. It only matters what happens when it's close. And so in this case, when it's close, it looks like it's going to be a value of -1. If I say that right here, y is -1. Okay. We can also talk about limits going from one side. So we have this idea of this limit as x is approaching a point from one side. So we'll call this, we'll say like this, for the example we have here. This is called a right-hand limit, and means approach 2 from numbers a bit larger than 2, but not less than 2. Okay. In the previous example, so in previous example, we could compute, let's say we did this, the limit as x goes to 2 from the right of the f of x. So what does that represent? That means we're at numbers a little bit larger than 2. So we're in this area right here. And what's happening? Well, in that case, my y value is very close to 2, so the limit's going to be 2. All right. We also have the limit as x goes from 2 to the left. So this is called left-hand limits. Okay. And that means we approach 2 from numbers a bit smaller than 2. And in the previous example, the limit as x approaches 2 from the left of f of x, what do we get? Okay, now we're approaching from numbers from this side here. Well, it's approaching 1. We're going this way, all right? Earlier, do this one really in purple. Okay, I mean, this one, when we were going from the right, we were approaching this way and we got the value of 2. Now we're approaching from the left and we get the values 1 right there. So this is going to equal 1, and this one was 2. Okay, we have those left-hand limits and right-hand limits there. All right. Now we have the next case, and this is the case where we have a 0 in the denominator. So we'll do this example here, example 4. Let's find the limit as x goes to 0, and we're going to go from right. So the limit as x goes to 0 from the right of the function x minus 2 over x. So what is that limit? Well, if as I get really close to 0 into this function here from the right, I notice that my denominator is getting really close to 0, but my numerator is getting really close to -2. So numerator is getting close to -2, denominator is getting really close to 0. Anytime you have a limit where you have a non-zero number over 0, means you have three possibilities. The limit in this case, as x goes to 0 from the right, of x minus 2 over x could equal one of the following three. It could equal infinity, negative infinity, or does not exist. DNE, sorry, does not exist. All right. How do I figure out which of these three it is? Those are the only three possibilities it could be. Okay, infinity, negative infinity, or does not exist. All right. So what do I do? Well, because it's a one-sided limit, it's not going to be does not exist. So in this case, it does not exist is not a possibility because I have a one-sided limit. So it's either going to be infinity or negative infinity. And so now I just need to figure out what is the sign on numerator and the sign in the denominator. If the sign in the numerator and the denominator over the denominator, if that equals a positive number, then I get positive infinity. If the sign of the numerator over the sign of the denominator is a negative number, then that means I'm going to get negative infinity. And how do I figure out that sign? I'm going to choose a number that's x is approaching 0 from the right. So I want to choose a number a little bit larger than 0. So we could pick the number 1. We could pick the number 1/2. We could pick the number, any of those numbers. Let's take 0.5. So if I do that, but choose x equals 0.5. So that's a little bit. It's a number that's larger than 0, and it's from the right of 0. Then I've got 0.5 minus 2 over 0.5. So that's going to give me a negative 1.5 over 0.5. And it doesn't matter what the number is, but what's important here is the sign. So this is a negative number. Okay, that means that the answer to the limit of this is negative infinity, because a negative number gives me the negative infinity. All right. Now this only works because I have a non-zero number over numerator over a 0 in the denominator as x gets really close to 0. Okay, let's look at it. Another example similar to this one. Okay, the previous one we looked at the limit as x goes to 0 from the right. Now let's look at the limit as x goes to 0 to the left. Okay, same function. What happens here? Again, as I get really close to 0, okay, the numerator when it gets close to -2, and should I say, as x gets close to 0, okay, from the left, the numerator gets close to -2, and the denominator gets close to 0. All right, so what does that tell me? So that means that my limit can equal one of two possibilities: infinity, negative infinity, or does not exist. And because it's a one-sided limit, does not exist, it's going to cancel out. So it's either going to be infinity or negative infinity. And just like before, we have to decide what's the sign x minus 2 over x as x approaches 0 from the left. Okay, a positive number or a negative number. So positive number or negative number. So I'm going to do just like we did before. We could choose a number that's a little bit large, a little bit less than 0. So it's choose x equals, let's say, negative 0.5. All right. When I do that, I'm going to get negative 0.5 minus 2 in the numerator over negative 0.5. And that gives me a negative number over a negative number, which is a positive number. So the limit as x goes to 0 from the left of x minus 2 over x is going to equal positive infinity. Okay. This only works if I have a non-negative number over 0 as x is getting close to there. The last case we have here, example 6, is I have the limit as x approaches 0 from both sides of x minus 2 over x. All right. So again, we see that we're going to we have a non-zero number over 0. So that means we're going to have three possibilities: negative infinity, or say positive infinity, negative infinity, or does not exist. Now, when you have a two-sided limit, we want to look at limit from both sides, and we already did that. So the limit from the right was negative infinity, and the limit from the left was positive infinity. So if these do not agree, or they're not the same, means does not exist. So the answer is does not exist. The limit as x goes to 0 of x minus 2 over x does not exist. Okay. Another example of this in my lecture notes, so you can look that over, get another example if you want to do that. But the key idea is if I have a non-zero number over, then it's going to be one of three possibilities, either infinity, negative infinity, or does not exist. And then you want to use approaches to figure out which one of those examples it will be. Now, a note here, okay? And negative infinity are not numbers, okay? Don't say that the limit, when we say that the limit equals infinity, it doesn't mean it equals a number, okay? The limit equals infinity tells us more information than that it doesn't exist. So what I'm saying here is if the limit, as in this case, as x goes to 0, the right of this equals negative infinity, the limit of this does not exist, okay? The fact that it equals negative infinity gives us more information. So if you could say, you would be correct if you say that this limit x goes to from the right not exists. That's correct. It doesn't exist. But by saying that it equals negative infinity, that gives us more information. So if you had a multiple choice question, you would never have the options of negative infinity and does not exist at the same time, because both of those are correct. All right. It's just that negative infinity is a better example, a better answer. It gives us more information. Same thing if it was positive infinity. So don't get confused by that. All right. The limit doesn't exist in all of these cases when I have a non-zero number over a zero number, but we get more information if we can figure out whether it's infinity or negative infinity. All right. Then one remark here, one last idea here is that if the limit of a function f of x equals infinity or negative infinity, then line x equals x naught is called a vertical asymptote, okay? So for example, if I had the function f of x equals 1 over x squared, all right? If I look at the limit of this one, it turns out the limit from the right is going to equal infinity, okay? If I look at that, then got a non-zero number over 0 as x gets close to 0. So it's going to be infinity, negative infinity, or does not exist. When I put in a number a little bit larger than 0, I get a positive on the top and a positive on the bottom, so it's positive infinity. I look at x going to 0 from the left of this, all right, I get a non-zero number over 0. So I have infinity, negative infinity, or does not exist. I put in a number a little bit less than 0. I get a positive on the top and I get a positive on the bottom again. So that's infinity. So this means then that the limit as x goes to 0 is infinity. The limit from the right is the same value or the same result as the limit from the left, and those are infinity. So then the limit from just 0 also is infinity. Again, this means the limit doesn't exist, but we get more information by saying that it equals infinity. And this means also have a vertical asymptote at x equals 0. And if I were to look at the graph of this function, okay, not something I would expect you to know, but I could use Desmos to graph it, okay? It's going to look like this. And so what's happening as x gets close to 0? Well, the graph is going off to infinity, okay? Right, it's going off to infinity. From the left, it's going off to infinity. Okay, the blue line's getting larger and larger and larger. Maybe it would be better if I just wrote that in blue. This is getting larger and larger, closer and closer to infinity, closer and closer to infinity. I have this vertical asymptote here, which is often represented as a dotted line going down, dot, 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 and that's that vertical asymptote x equals 0. And why do I get x equals 0? Because that's what was the limit I was looking at as x goes to 0 there. All right. Hope that helps. Great day.